Greetings, ladies and gentlemen. My name is Muhammad Khatami Rafsanjani, and joining me as co-authors for this research are Mr. Pahala Dominiku Sinurat and Mr. Dedi Irawan. We are from Faculty of Mining and Petroleum Engineering at Bandung Institute of Technology, Indonesia. And today, as a representation of my team, I'm delighted to present our research at the International Conference on Geoscience and Earth Resources Engineering 2023. The title of our presentation is Advancing Relative Permeability Prediction in Water Gas Reservoir Systems, a comparative study of models utilizing porous plate capillary pressure measurements. In the field of reservoir engineering, accurate estimation of relative permeabilities is crucial for optimizing oil and gas recovery strategies. Relative permeabilities describe the fluid flow behavior in porous media and play a significant role in reservoir characterization on production forecasting. What becomes the background of our study is the challenge of understanding and predicting relative permeabilities, which is a key focus for reservoir engineers. Our research directly addresses this important aspect, aiming to enhance our knowledge and method in this critical area. In this study, we focus on evaluating existing models for estimating relative permeabilities in a gas field located in Indonesia, which features a water gas reservoir system. The selection of these models will significantly impact the effectiveness of reservoir management and the overall success of hydrocarbon recovery operations in the specific field. The relevance of our study lies in addressing the practical concerns of reservoir engineers and decision makers, offering insights into the most suitable approach for tackling the challenges presented by the specific reservoir setting. The purpose of this study is to estimate relative permeability using porous plate capillary pressure measurements and conduct a comprehensive evaluation of several comparative models, including the Ross-Bruce model, Corey model, our modified Corey model, and analytical solution model known as modified Brooks-Corey model, specifically applied to the water gas reservoir system. By subjecting these models to thorough analysis and examination, we aim to identify their strengths and limitations, enabling us to pinpoint the most robust and accurate approach for predicting relative permeability in this water gas reservoir environment. Now that we have provided an overview of the background, relevance, and the purpose of our study, let's shift our focus to the details of our experimental methodology. In this section, I will take you on a historical journey, exploring the evolution of methodologies used in predicting relative permeability. By examining the historical perspective, we can better understand how these methodologies have evolved and how they have shaped our current approach to predict relative permeability in this gas field. In our study, we employ a groundbreaking concept known as the leverage J function, which was introduced by Leverett in 1940. This concept plays an important role in normalizing capillary pressure data and characterizing the relationship between capillary pressure and fluid saturation in porous media. The leverage J function is mathematically defined as you can see in the slide. By utilizing the leverage J function, we can determine the capillary pressure values, which is crucial for understanding fluid flow behavior in this gas field. This function helps us normalize capillary pressure data and derive dimensionless value that aid in the accurate estimation of relative permeability. We integrate the determined capillary pressure value into the Ross-Bruce model, one of the comparative models under evaluation in our study. The combined analysis of the leverage J function and the Ross-Bruce model allows us to predict the relative permeabilities of water and gas phases within the reservoir. Now that we have delved into the significance and mathematical foundation of the leverage J function, let's further enhance our understanding of fluid flow behavior in the reservoir by incorporating another vital concept, the Purcell relative permeability. Purcell relative permeability was introduced by Purcell in 1949. It's a method for estimating relative permeability which utilizes capillary pressure data from mercury injection curves, applicable for two-phase flow like oil-water or gas-water systems. By analyzing the relationship between pore size distribution and capillary pressure curves, it quantifies relative permeability for different fluid phases. Virtual relative permeability model for wetting and non-wetting phase is defined as you can see in the slide. The virtual relative permeability model laid the groundwork for Bourdin's advancement in fluid flow characterization, incorporating tortuosity effects within capillary tubes for the Bourdin relative permeability model. Now, let's delve into the Bourdin relative permeability model and discover how it contributes to our efforts in accurately estimating relative permeability. Moving forward in our historical journey, we arrive at a crucial moment in fluid flow characterization, the Bourdin relative permeability model. In 1950, Bourdin and his colleagues made significant advancement to the Purcell model by introducing the concept of tortuosity within a bundle of capillary tubes. This breakthrough offered an alternative approach to comprehending the complex nature of fluid movement within porous formations. Bourdin's contributions were revolutionary as they involved defining tortuosity in the relative permeability term for both wetting and non-wetting phases. By incorporating tortuosity factors, Bourdin model provided valuable insight into the flow characteristic and phase distribution within the porous medium. The Bourdin relative permeability equation for the wetting phase and non-wetting phase can be seen in this slide. According to Bourdin, the tortuosity factor of wetting phase and non-wetting phase is defined as you can see in the slide. By substituting the definition of tortuosity factor and assuming equilibrium saturation equals to 0 and minimum water saturation as condensed water saturation or irreducible water saturation, the final relative permeability equation for water is highlighted by the blue marker, while the equation for gas is highlighted by the red marker. Building on the pioneering work of Bourdin, the Bourdin relative permeability equations have laid the foundations for the development of the Wiley-Gardner relative permeability model and Corey relative permeability model. Now, let me explain briefly about Corey relative permeability model first. In 1954, Corey developed the Purcell-Bourdin relative permeability equation by introducing normalized water saturation term and defined capillary pressure as you can see here. For gas equation is highlighted by the red marker and for water is highlighted by the blue marker. The introduction of the term normalized water saturation by Corey in the Purcell-Bourdin relative permeability equation holds significant importance as it serves as a crucial basis for the development of our modified Corey model. Let's begin by exploring the Wiley-Gardner relative permeability model first before we move on to our modified Corey model. In 1958, Wiley and Gardner introduced equations that are fundamental for estimating relative permeability in multi-phase flow within porous media. These equations are particularly applicable to analyzing scenarios involving two-phase flows, with a specific focus on the relative permeabilities of the wetting phase and the non-wetting phase. By modifying the integral limit in the Purcell-Bourdin equation, the Wiley and Gardner model was developed to represent relative permeability as a function of capillary pressure, which can be defined as you can see in the slide. This Wiley and Gardner relative permeability model forms the basis for subsequent models such as the Rosebrush model and our own modified Corey model. Now, let's dive into a captivating part of our study, our very own modified Corey model, specifically designed for this water-gas reservoir system. The modified Corey model presented in this study represents an innovative approach that combines elements from the Corey and Purcell-Burdin models. By incorporating the modified Purcell-Burdin equation and utilizing the Corey normalized water saturation term, we define the relative permeability equations for water-gas reservoir systems as follows. To enhance the model's accuracy, we introduce water and gas constants, denoted as A and B, respectively, which serve as the endpoint values in the equations. As a result, we obtain the final equations for water and gas relative permeability. And the most important part thing is the parameters A, B, NW, and NG values are estimated by utilizing numerical approach. Okay, on the next slide, we will thoroughly examine the analytical prowess of another widely used model, the analytical solution model. The analytical solution model, known as modified Brooks-Corey relative permeability model, is a commonly employed in numerical simulators. This model plays a crucial role in understanding fluid behavior in our reservoir. The analytical model equation for water gas reservoir system is defined as follows in the slide. This model is constructed using parameters derived from experimental relative permeability data. The exponents of gas and water, NW and NG, are determined by utilizing least square approach to match the relative permeability results from the experimental data. While the endpoints gas relative permeability at irresidual water saturation and water relative permeability at residual gas saturation have fixed values and determined based on the endpoint of relative permeability from experimental data. In contrast, our very own modified Corey model is built upon water saturation values obtained from capillary pressure measurements. This distinction sets the stage for an intriguing comparison between these two models, which we will discuss later. Now, let's move into the results and discussion about the models we use to predict relative permeability for this water gas reservoir system. In this study, we analyzed experimental capillary pressure data from a gas field with a water gas reservoir system in Indonesia, aiming to understand the correlation between relative permeability and capillary pressure. We explore various models, including the Rose-Bruce, Corey, and our modified Corey model. Furthermore, we conducted a comparison between our modified Corey model and the widely used analytical model, the modified Brooks-Corey model, to assess our model accuracy in predicting relative permeability from the capillary pressure data. Throughout our analysis, we utilized the Lagrange function correlation, especially in the Rose-Bruce model, to establish the relationship between capillary pressure data and relative permeability. As a result, we obtain valuable insights into the fluid behavior within the porous media and identify the most suitable model for characterizing fluid flow behavior in the studied water gas reservoir system. Now, let's dive into the results of the Rose-Bruce model and see how it performs in capturing the relative permeability behavior based on the capillary pressure data. In 1949, Rose and Bruce conducted a comprehensive investigation on the sensitivity of rock properties and their influence on the characteristic of mercury injection capillary pressure curves. Their study revealed the dependence of measured capillary pressure on pore configuration, rock surface properties, and fluid properties. Furthermore, Rose and Bruce made a significant advancement by integrating their insightful modification to the Lagrange function into the Wiley-Gardner relative permeability equation. This improvement allowed for the generation of relative permeability saturation profiles, providing profound insight into the fluid flow behavior within porous media. The relationship between the J function and water saturation derive from derived from capillary pressure measurements in a laboratory experiment serve as a fundamental basis for establishing the crucial correlation between normalized capillary pressure and water saturation. This correlation can be clearly expressed by the following power law equation for capillary pressure as a function of water saturation, as you can see in the slide. By substituting the capillary pressure equation into the Wiley-Gardner relative permeability equation, we can derive the Rose-Bruce gas and water relative permeability equations for this gas field. The final equations are defined as follows. For water, relative permeability is highlighted by blue marker, and for gas relative permeability is highlighted by the red marker. This figure presents the comparison of Rose and Bruce relative permeability model with experimental relative permeability curve. From the comparison, it's evident that the estimated relative permeability values for both the wetting and non-wetting phases obtained using the Rose-Bruce model do not exhibit a close fit to the experimental relative permeability results. The considerable deviation between the estimated and experimental relative permeability suggests that the Rose-Bruce model is not well suited for accurately predicting the relative permeability behavior in the specific gas field. These findings highlight the limitation of the Rose-Bruce model in capturing the complex fluid flow characteristic within the studied water-gas reservoir system. Having gained valuable insights from the comparison of the Rose-Bruce model with the experimental data, it becomes evident that a more accurate and robust approach is necessary to characterize the fluid flow behavior within our water-gas reservoir system. Considering this, we shift our focus to the Corey model. Let's delve into the details of the Corey model and explore its applicability in predicting relative permeability for this gas field. The comparison between the Corey relative permeability model and the experimental relative permeability curve clearly indicates that the estimated relative permeability values for both the wetting and non-wetting phases obtained using the Corey model deviate significantly from the experimental data. This finding suggests that the Corey model is also not well suited for accurately predicting the relative permeability behavior in the specific gas field. As we have examined and compared the Rose-Bruce and Corey models, both of which demonstrate limitations in accurately predicting the relative permeability behavior in our water-gas reservoir system, it becomes apparent that a more customized and resilient approach is required. In response to these challenges, we present our innovative solution, the modified Corey model. Let's now shift our focus to the modified Corey model and uncover how it addresses the shortcomings of the previous models, providing us with a more precise characterization of fluid flow behavior in our reservoir. In the modified Corey equation, the use of normalized water saturation is crucial. To obtain this, we perform a linear regression to establish the correlation between normalized water saturation and water saturation. Initially, we input the parameters' initial values, which we can guess as any value, for example, 1, into the relative permeability equation. We then apply a numerical optimization technique to generate new parameter values that better fit the experimental relative permeability data. The comparison of modified Corey relative permeability model with experimental relative permeability curve clearly demonstrates the accuracy of our modified Corey model in predicting relative permeability values that closely align with the experimental data. Through the validation metric MSE, or mean square error, we evaluate the performance of the model. The MSE for the non-wetting phase relative permeability between the modified Corey model and the experimental result is 6.24 times 10 to the power of minus 5, while the MSE for the wetting phase between the two models is 1.10 times 10 to the power of minus 6. The modified Corey model demonstrates improved accuracy in predicting the relative permeability behavior in the studied gas field. making it a more reliable and robust approach compared to the previous models. With great success in developing and validating our modified Cori model, showcasing its improved accuracy in predicting relative permeability behavior. Our focus now shifts toward exploring another widely used approach, the analytical solution model. In the next slide, we will delve into the fundamental principle of the analytical solution model and conduct a zero comparison with our modified Cori model. Through this analysis, we seek to gain a deeper understanding of the strengths and limitations of our modified Cori in predicting relative permeability from capillary pressure data compared to analytical solution model. The analytical solution, also known as the modified Brooks-Corey model, is widely utilized in numerical simulators for characterizing fluid flow in porous media. Upon comparing the analytical solution relative permeability model with the experimental relative permeability curve, we observe its higher accuracy in comparison to the Rose, Bruce, and Corey models. As a reminder, these parameters are fixed values obtained from the experimental permeability curve. To validate the model, we employ the least square approach to estimate the values of NW and NG, and then calculate the mean square error as the validation metric. The MSE for the non-wetting phase relative permeability between the model and the experimental data is 6.27 times 10 to the power of minus 5, while for the wetting phase it's 4.12 times 10 to the power of minus 6. These low MSE values provide compelling evidence supporting the model's effectiveness in accurately estimating the wetting phase relative permeability and non-wetting phase relative permeability. After thoroughly exploring the details and examining the performance of each model, let's now move into the conclusion of our comparative study analysis. Our thorough evaluation of the Rose, Bruce, and Corey models exposed notable deviations, making them unsuitable for accurately estimating relative permeability in this gas field. In contrast, the analytical solution, known as modified Brooks-Corey model, determined through a least square approach, offered a viable alternative with higher accuracy. However, the need for fixed and X-point value in this model may limit its ability to capture system complexities, potentially leading to inaccuracies in certain cases. Our modified Cori model emerged as a promising solution for relative permeability prediction in this gas field. Not only does this model accurately predict relative permeabilities that closely align with experimental data, surpassing other models in performance, but it also boasts enhanced flexibility by eliminating the requirement for fixed endpoint values like in the analytical solution model. These findings contribute valuable knowledge to the field of reservoir engineering and set the stage for further studies. Moving forward, future research could focus on refining our modified Cori model and incorporating additional factors to capture the complexities of different reservoir systems more effectively. For instance, this new method provides an additional parameter for the relative permeability model in the history matching process in reservoir simulation. Such advancements hold immense potential for advancing our understanding of fluid flow in porous media and further improving reservoir characterization. Thanks.